Okay, so let's consider this one. And this one here, if you actually do the integral test, so 1 to infinity for 1 over x to the power p dp, so dx, we can show that this here converges provided that p is greater than 1. Okay, converges provided that p is greater than 1. So this I actually already did in 7.8 in your textbook. It was one of the questions of improper integration. So I'm going to do it again. If you already know it, you can just fast forward it and come to the conclusion that since this one is, right, this one is converging, this sum will also converge. Okay, very simple. Converge provided that p is greater than 1. Now we call this, give it a special name because it happens a lot, p-series test. Okay. So you just mentioned that p-series, by p-series test, this is converging when you're justifying your answers from here and on. Okay, for this, for the integration, it's same as x to the power minus p, which is the same thing as x to the power minus p plus 1, 1 over minus p plus 1. Okay, and it's 1 to t, where t is approaching infinity. Okay, so let's plug in t. And let's plug in 1, and you just get this. Okay. So what's happening to this as t approaches to infinity? And that totally depends, right? If the t is on the numerator, it will diverge. To make sure that it converges, right, this needs to be a fraction, meaning minus p plus 1. The exponent needs to be negative. You have to make sure that's negative. Negative. So we get minus p is less than negative 1, which means p has to be greater than 1. So when p is greater than 1, the integral is converging. Okay, again, because now by integral test we can say that this series is converging as well.